Midpoint integration. So what is midpoint integration? In midpoint method, you are also using the rectangular method to evaluate, of course, that's the numerical approach, to evaluate the area underneath the curve. However, instead of picking the first point encountered on the curve, which is on x, we are picking the height of the rectangle where x is at half of the distance between x and x plus step. In other words, where x is in the middle, that's the height of the curve that we are taking for the height of the rectangle to be multiplied by the step. Now you would think that you would have an excess here, okay, which is an error in calculation, because this does not belong to the part of the area underneath the curve. However, if you look to the right, you have a void area here that's not covered by the rectangle, that is underneath the curve but would not be included in the area of the rectangle. Looking at this curve, you notice that almost this area that we missed here is the same area that is covered by the rectangle to the left. In other words, that void that's not evaluated by the area of the rectangle is actually covered by this chunk of the rectangle to the left, where the area that is covered is above the curve. Okay, so this area is almost the same as this area. Thus, the area of this rectangle amounts almost to the same exact area beneath the curve within this interval. Of course, as you narrow down the step, you would get a higher resolution and a more accurate result. Now let's jump into practice. Of course, as a review, I need to write the function for a polynomial equation. This is what we've been using. So, and by the way, I've included math.h library. Double, and we will call this function f, like fx, all right? Double a, double b, double c, and double x. What these numbers mean, it is the form of equation which is ax squared plus bx plus c. Okay, where of course x is the variable and a, b, c are the constants of the polynomial equation. Return for each x the value of f, where fx, which is equal ax2 bx plus c, or return a times pow x2 plus b times x plus c. Power, of course, the power, raising x to the power of 2. Next, I need the double function for integral evaluation. So double midpoint int or integral, also double a, double b, double c, and double b1, which is the first boundary of the integral, double b2, and double n. Here, we're going to evaluate the step in a different way. N is the number of divisions or steps underneath the curve, which is equal to double step equal b2 minus b1 together divided by n, or the number of parts, the number of chunks that would define the resolution of this integral. Okay, n is to be designated by the user. Now, double x is equal b1. This is where the integration should start at b1. And double s is equal 0. That will keep adding up each area of the integral as the interval moves from x to x plus step to, x plus step, etc. We need to loop while x less than b2 minus step, which is the point where x sits at the last interval. This is where b2 minus step is. So we evaluate the last area, the last rectangle, and then we break out of the loop. So s plus equal the function f a, b, c, and I need x plus step together divided by 2 times step. Then I need to increment the x of one step to move the interval, and finally return s, which is the sum or the integral. Now we go down to main. Double b1 equals 0. Here I need to declare the different boundaries. b2 equals 0. I'm initializing them at 0. And n equal 10. Actually, they're gonna be updated by the user. Let's prompt the user to enter for us these different values. Enter the respective boundaries, b1 then b2 respectively. Scanf %lf because it's a long float, and ampersand b1. Same thing for B2, scanf, lf. Then I'm gonna prompt the user to enter the number of divisions. Printf \n, enter the number of divisions, or steps \n, scanf, %long float, and %n. Finally, double sum equal midpoint integral. We are calling the function y00 because we are using y equal x2, b1, b2, and n. And let's display the result. Double f sum or area using midpoint method for x2, y equal x2 is %f and \n sum. Let's display the result. Okay, building. Okay, enter the boundaries between 0 and 2. The number of divisions, let's be 10,000 for a higher resolution, a more accurate result. And the result for the integral or sum or area using midpoint method for y equal x2 between 0 and 2 is 2.6667. Actually, it is very accurate. That's a very effective method. Okay, thank you for watching.